Okay, hello. So this video is the second video about simple harmonic motion as it's taught in the Further Mechanics, Further Maths A-Level course. In this video I'm going to show some examples. Hopefully I'll be able to get through 4 examples of various types of exam questions. But before getting on with the examples, let's review. So in the first video I tried to give some explanation of the importance of simple harmonic motion, some justification, and how to solve the most basic types of problems doing calculations. But I think before we go on to the exam questions I need to first look at the syllabus and then also maybe make a list of the key equations that we're going to need. So the syllabus has quite a long description here of what you need to know about SHM, definition, period, amplitude, equation of motion, that's the basic equation of motion that we discussed, and calculating period amplitude. Also the last section is talking about approximations, in particular small angle approximations or binomial approximations. So that's obviously something you can read later, but now let's make a list of the key equations. So number 1 is the defining equation of SHM. Defining equation of SHM, d2x by dt squared, where x is a displacement variable, is equal to minus n squared x, where n can also be written omega, the angular velocity of the associated circular motion. So no need to say any more about that, you should already know that. Second most important equation is the general solution of that, which is x equal to the amplitude times cosine or sine nt plus epsilon. So here we already discussed this as a general solution for the above equation. Alright. Third equation you need, maybe the third most important, is the relationship of the period to the quantity n. So t is 2 pi over n. Now, fourth equation, I think I will write the formula for velocity. So velocity is dx by dt, or x dot, and this can be derived directly from this, so we get minus na sine nt plus epsilon. Now you won't often use the equation for velocity in that form, just sometimes it's useful to know. What's more common, and this is not obvious, but what's more common is to make a relationship between v and x. So v squared is n squared a squared minus x squared. Now I won't bother to derive this formula, it can be derived by looking at the associated circular motion most easily, but also just using calculus, the previous equations. But this is the kind of equation it's really just worth remembering. And why is it useful? Because it makes a direct relationship between v and x, between velocity and displacement. Note, for example, that the maximum occurs when x equals 0. So when x is 0, we get the maximum velocity, and it's na. Notice also that the maximum acceleration, which is x double dot max, equals n squared times a. That, of course, I mean magnitude. The maximum magnitude of acceleration is n squared times a, where a is the amplitude. That's obvious from this equation here. Okay, so I've rushed through those. Most of them you already know. You may already know all of them. But all of them will be useful in different situations as we look at examples. Okay, so I have 4 examples. Now the first 2 exam question examples are not actually from the Further Maths CIE exam. They're from the M3 component of the EdExcel Mathematics A-Level. But they cover the same concepts in a slightly more basic way, so I thought they would be useful. So let's look at the first one. Here's the first example. As usual, please do take a look at questions and try to try to solve them on your own if you can, without my help. I think, yeah, okay. So this is the question. A particle P with mass given as 0.8 is attached to one end A of a light elastic spring OA of natural length 0.6 meters and modulus of elasticity 12 newtons. The spring, very important, not string, but spring. So we're talking about this situation. I'll just draw a small diagram here. Spring, and at the end we have a mass, and that mass is called P, and it's 0.8 kg. And that's a sort of schematic diagram. So what we're saying is that it's placed at a point B and then released. Now B is 85 centimeters. So this is 0.6 meters, the natural length, and B is a further 0.25 meters away. So obviously when it's released it will snap back this way, the motion will be this way. Now of course if this were a string with a T instead of a spring with a P, we would not get SHM. If this were a string we would have this situation, an elastic string. We released P, it would travel backwards, and then when it reached the natural length, the tension force would disappear, and then the object would simply continue to travel towards A. So that wouldn't be SHM, at least not for the whole motion. But in the case here, P is on a spring, so when P reaches a position closer to O than 0.6 meters, we get a compression force, and P will be pushed back this way, so we will in fact get an oscillation motion like this. Yeah. And we know that because P is released at this point, that means its velocity at this point is 0, which means that the amplitude of the oscillation will be equal to exactly 0.25 meters. So that's an important principle to understand, which is that if an object is released at a certain point and then performs SHM, the amplitude of the SHM will be equal to that displacement that you had at the beginning. In other words, the displacement at the beginning will be the largest displacement. And you can understand that easily from the point of view of energy, because if you release the object at this 0.25 meters, it has 0 kinetic energy at that point. So according to conservation of energy, it will have 0 kinetic energy again when it reaches that point a second time, and continuing will oscillate between those positions. So that's the basic idea. Now let's draw a more accurate and useful diagram and start answering the actual numerical questions here. So I'm going to use a little bit of space down here. So the spring is placed, OB is 85, released from rest. And we're going to prove that we've got SHM. So here we go. Let's draw O here. Let's draw a horizontal line. Okay, so let's say this is B, and we'll draw a certain position. I guess it's around here. This is 0.6 meters. This is 0.25 meters. Okay. Now we notice that the equilibrium position of the particle is here. I'll give this point a name. This can be called point A, maybe. No, sorry, this can be called point D. And so I'm going to define a variable y such that y is 0 at D and increases to the right, increases away from O. And now I'm going to show that the motion of P will be simple harmonic if it's released from B. So I'll choose another position E at a general point in the motion, say E. We can consider the force on P. Well, it will just be a tension force T, which will be lambda times the extension divided by the natural length. Now the extension will just be y. So y is defined to be 0 at D, and D is where the extension is 0. So dE equals y is the extension. And this tension is negative because y is defined to be positive in the rightward direction. Now lambda was 12 and the natural length was 0.6, and that will be equal to m times y double dot. And as I described in the previous video, it's easy to justify that y double dot, the acceleration, or the second derivative of the displacement, it doesn't depend which point you take as the origin. Now the mass was 0.8, so therefore I have something like this: y double dot is minus 12 over 0.6 times 0.8 times y. So let's do a bit of arithmetic here. I've got 3 times 4 over 5 times 5, so that's minus 25y. So therefore P performs SHM with D as centre, and period is 2 pi over n, which is 2 pi over the square root of 25, which is 2 pi over 5. So that's what was required. So I hope that's pretty clear. As usual, it's very useful to define your displacement variable as being 0 at the equilibrium position. Now, to be clear, I didn't mention in this that when P, so let's say this is P here, maybe I'll put a big thing there. So when P goes to the left-hand side of D, T is still obeying this same equation, because when P is over here, let's say, the tension force is not anymore a tension force in the spring, it's a compression force. Remember here, it's not a string, but a spring, and springs can be compressed, which means that they will push away from the compression towards D. So there's not much more you can write about that in the answer, just maybe make a note that it's still true when y is negative on the left-hand side of D. Okay, so that's the first part of the question. I need some more room here. Let me make a new page. So we've done the first part, and that was worth 5 marks, so be aware if something's worth 5 marks, you have to put some effort into it. Let me say diagram, yeah, it's very important to have a good diagram. Now part B says find the greatest magnitude of the acceleration of P during the motion. Well, because we just said that y double dot is minus 25y, I hope it's obvious that, as I said at the beginning, the maximum acceleration occurs at the endpoints. So that will be maximum magnitude is 25 times 0.25. So that's 6.25 meters per second squared. Notice here I'm using SI units, meters and seconds. So in case that isn't obvious to anyone, when an object is moving between two extreme points, acceleration is always proportional to displacement. So the largest displacements, which occur here and here, give the largest accelerations. Now, third part, 2 seconds after being released from rest, P passes through the point C. Find the speed of P as it passes through C. Sorry, I seem to have... Oh, I see. I've put an extra page in the wrong place. Maybe I can delete this page. How do I delete a page? Okay, good. So if I move up here, that's better. So I'm being asked now to find the speed of P after 2 seconds. Let me think about the easiest way to do this. Well, okay, I know the basic equation. The basic equation of the motion is y. Oops, sorry. Is y double dot equals minus 25y. So the general solution for y is y equals the amplitude times the cosine of n, which was 5, t plus epsilon. Now, a is the amplitude, but we already said at the beginning that because it was released from rest at b, that means the maximum displacement is at b, which was 0.25 meters. So the amplitude is 0.25. So n is 5, we've already written that here. But what about epsilon? What value should we use for that? Okay, this is easy once you understand it, but if you've never seen this before, it might be confusing. Remember, the idea of epsilon is phase shift. So the motion that we're looking at could be drawn on a graph like this, or it could be drawn, I don't know, like this. Sorry, that's not very good, but you get the idea. Shifting the graph, or it could be drawn as a sine wave like this. So the wave can be shifted to the left or right. And it's really a matter of choice, isn't it? Because after all, what time is time zero? It is whatever you say it is, yeah? But we know that in this question we're told that when t equals 0, y is plus 0.25. Y is at the maximum point. So in other words, it means that we're reaching y equals, let's say, so y of t equals 0 is equal to 0.25, but that's equal to 0.25 a times cosine 5t plus epsilon when t equals 0. So in other words, 0.25 cos epsilon equals 0.25. So epsilon is 0. So we can say that the correct specific solution to this equation in this question is y equals 0.25 cos 5t. So it's worth remembering perhaps that when a particle starts its motion at the extreme point, or let's say at the maximum point of displacement, then the particular solution will have epsilon equals 0. So epsilon equals 0 is the correct particular solution. Well, then it follows that if we want to know the value of the speed, well, there's two ways to do it. Let's do it one way. One way would be to say, well, when t equals 2, y equals 1/4, 0.25 times the cosine of 10, and the speed will be found using the formula n squared a squared minus x squared. In this case, the displacement variable is y, not x. So I've got v squared equals 5 squared times 1 over 4.25 squared minus, what was this? Right, 1 over 4 squared cos squared 10. So here you could get a formula for v and use a calculator. There is a second way to do it, and I suppose since we're learning it's worth thinking about both ways. The other way to do it is to find the velocity by differentiating the displacement. Well, that should be minus 0.25 times 5 times the sine of 5 times 2. Remember, t is 2 here. So we differentiate y, we get this formula for y, and this is the value of y, the value of the velocity, the derivative of y with respect to time, when t equals 2. So you can see that in this case it's slightly easier to solve the problem in this way, because we don't have such a complicated formula here. Well, actually, you can see it's obviously the same formula. This gives v equals 5, 1 over 4, sorry, 1 minus cos squared 10, which is square root 1 minus cos squared 10, which is sine 10. So you can verify it's the same formula. Now I think I probably wrote that down, that numerical answer somewhere, so just for completeness I'll try and find it. 2.6. No, sorry, that's a different question. 0.68 meters per second. So forgive me if I calculate this wrong, but I'm pretty sure that is equal to 0.68 meters per second. Okay, so that's how you can calculate the velocity if you know. Notice it's basically saying that we can calculate the velocity at any time as long as we know the amplitude, the starting value of y, and the period. So let's give a tick there. We've done those parts. And the last part, state the direction in which p is moving 2 seconds after being released. So this is the same time, 2 seconds, and they're just simply asking the question, which direction is it moving? Well, of course, the reason they're asking that is that if you had used this formula to find the speed, which is absolutely correct, it won't tell you the direction. This is an equation about speed, whereas this equation that I wrote here is an equation about velocity, so it gives you the speed. Okay. Now don't jump to conclusions. You see a minus sign here, you might think, oh, it's negative, so it's going to the left. Remember, our diagram looked like this. After 2 seconds, we know that the period is 2 pi over 5, which is more than 1 second. Slightly more than 1 second, isn't it? So after 2 seconds, we've almost completed 2 periods. Now remember, a period means we go all the way to maybe here. So let's use another colour. Period means we go all the way to here, then all the way back. That's a whole period. Now this is almost 2 whole periods, so it actually means we're going to go all the way back and then all the way to maybe here or something like that. Obviously don't draw that on your diagram because that won't help people, but I'm just showing you that for visualization. So we can already just kind of guess, because this number is like a bit more than 1, and 2 seconds is 2 seconds is not quite 2 whole periods, yeah. So we can already guess it's moving to the right on this diagram. But we don't have to guess. We can look at this formula and just calculate carefully. So y dot 2 is minus 5 over 4 times sine of 10. Now sine of 10, if we just remember what sine looks like, this is 2 pi. Now 2 pi is about 6. You may actually need a calculator to do this. What's 3 pi? 3 pi is just slightly less than 10. Okay, so what we're talking about with sine 10 is we get a number that's less than 0. Oops. Let me just check that. Is that right? 3.14. Yeah, 3.14 times 3 gives you 9.4 or thereabouts. So sine 10 is a negative number. So if sine 10, is a negative number, it follows that this quantity is positive, because that's negative and negative. So if this quantity is positive, then the direction of motion is moving away from O, and that's the answer. Okay, so the last part, the answer is moving away from O towards B. Yeah, there we go. Notice it's only 1 mark. Alright, so that's a good example of just you doing basic calculations of an SHM motion. The second one is similar, maybe it has just a little extra trick to it. A piston P in a machine. So again, you can please read this and try it on your own if you want. A piston P in a machine moves in a straight line with SHM about point O, which is the center. The period is pi. That's a bit unusual, but okay. The period is pi. When P is 0.5 meters from O, the speed is 2.4. So there's our data. How can we find the amplitude? Well, I hope you remember that I told you at the beginning the reason this equation here is very useful is because it makes a simple map between the velocity, or the speed, and the displacement. So we can use that. So here we can use v squared equals n squared a squared minus x squared. So v equals 2.4 when x is 0.5. But what about n? What's n? Well, n is 2 pi over t. And t is pi, so n is 2. So this gives us the calculation, which I'll just do a little bit lower down here. This gives us the calculation 2.4 squared equals 2 squared a squared minus 1/2 squared. Okay, so this is a bit of fiddly numbers here. You can use a calculator if you want. Yeah. So you get something like, if you do the arithmetic, you get something like a squared equals 6 over 5 squared plus 1 over 4. So that's 25 and 4, so I'm getting 4 times 36, which is 144 plus 25 over 100. So this is 169 over 100. So it's so A is the square root of that, which is 13 over 10. So the amplitude of the motion is 1.3 measured in meters. Oops, sorry, we did this one, not that one. So we calculated the amplitude as 1.3 meters. So then it says find the maximum speed during the motion. Let me just make some more room here. So now it says find the maximum speed during the motion. Well, again, this is a question of remembering the right formula. To find max speed, you can reuse this equation when x is 0, because when we perform SHM we go backwards and forwards. The fastest speed is in the middle there. So the fastest speed occurs when x is 0, That's the maximum kinetic energy, and so that's just NA. So that's 2 times 1.3, 2.6 meters per second. So that's the second part. Now let's find the maximum magnitude of the acceleration of P during the motion. Again, like all these steps, I showed you the right formula at the beginning. Maximum acceleration, let's say x double dot maximum acceleration would be n times so what am I saying? N squared, sorry, times the a. Yeah. Based on x double dot equals minus n squared x. So maximum x, which is a, gives maximum acceleration, which is 4 times 1.3. So that's 5.2 meters per second squared. Okay, well these first 3 parts were good practice, but they weren't very interesting. But it's the last part of the question that's definitely the most important. So let's find the total time. I've got to read this carefully. The total time in seconds in each complete oscillation for which the speed is greater than 2.4. Okay. Now, the way to understand this is to realize that we've got periodic motion. We've got a sinusoidal oscillation in position. So the picture is this, right? Sorry if my sine wave is not very good. Now, of course, each period, so here's one period from here to here, here's another period, and so on and so on. Each period is exactly the same in all respects, yeah? So however long we spend, well, okay, in this question we're only talking about one oscillation, but we could be talking about any number of oscillations. In each oscillation, there will be a certain period of time when the speed is bigger than 2.4. Sorry, what was the maximum speed? 2.6, yeah, 2.6. So that's rough, a rough diagram. I'll draw a neater one in a minute, but the idea is, suppose this is 2.4 here, and suppose this is minus 2.4, and this is velocity. Remember, not only does the displacement obey a sinusoidal oscillation, but so does the velocity. Well, it means that during this whole period, the speed is bigger than 2.4, yeah, and the same here. So if we want to be more concrete and physical about it, we imagine here's the center of the oscillation. Now we know the speed is 0 at the ends, but we also know that the speed is its maximum, which is 2.6 meters per second in the middle. Now it can be either plus or minus because it goes both this way and this way. But there's a certain region in the middle here, isn't there? All through this region, the speed will be bigger than 2.4. And that will correspond on a graph of velocity against time to certain regions here and here where the speed is bigger than 2.4. Okay, so that was all sort of rough drawing, but I'm going to draw more carefully now a diagram of the velocity as it varies with time and show you how to answer this type of question. So I'm going to need to spend a moment setting up a graph here. So my y-axis will be velocity, and what am I doing? My x-axis, which I'll put in the middle, will be time. So let's see what we can do here. Here's time, here's velocity. Now I know the maximum velocity is 2.6, so obviously the sort of minimum velocity, if I can draw it roughly the same place maybe, is minus 2.6. And now the interesting point is that I don't need to worry about where to start this graph. Should I start the curve here or here or here, and then, you know, so I can draw a sine curve or I can draw a cosine curve, but interesting point is it won't really affect the answer. So maybe I can come back to that if you didn't completely understand me. let me try and draw as carefully as I can a kind of bounding set here. So these horizontal lines will represent the maximum and minimum points. And I'm going to draw as best I can one complete wave. Yeah, just one complete wave should be fine. So suppose this is the end point, just for interest's sake. The period is pi, so this number here is actually pi. Okay, and so let's say pi over 2 is somewhere in the middle. So if I drew a sine wave, it would be something like this. Okay, not very good, but never mind. That's not bad. So what I'm saying is that if we were to write velocity as a function of time, in this case, we know that the value of n was 2. The value of n was 2. The amplitude of velocity is the velocity sine wave is 2.6. The n is 2, so I can write something like 2.6 sine 2t. Now you might be wondering, why is there no epsilon? Why is there no phase shift? You remember this idea, a cos nt plus epsilon equals x, yeah? And you're probably thinking, well, why did he just ignore this and just pretend it's a sine curve? Why is there no minus sign? You know, all this stuff. Well, that's all true, but the point is that every wave is the same as every other wave on this curve, because what I'm interested in is the proportion of the curve which obeys a certain principle. Okay, so let me read the question again. The total time in each complete oscillation for which the speed of p is greater than 2.4. So all I have to do is mark on this graph 2.4 and importantly minus 2.4 because it's speed that we're interested in, not velocity. And if I draw in another color a line here, I'm not sure if I'm going to be able to straighten that one out. No, I think that's a bit too much to ask, isn't it? I'll try and draw reasonably carefully a line here. Okay, those are supposed to be horizontal lines, so forgive me for that. So looking at this picture, we're asking ourselves for what period of time, maybe I can even write this, for, let's say, for how much of one period is modulus of v greater than 2.4, the speed. Yeah. So we're interested therefore in maybe using another color. We're interested in this part of the graph and this part of the graph. How much of the time occurs there? So we need to link it back to time, don't we? Let's put this number here as t1, and I might even go a bit further and draw another line there, another line there, another line there, another line there, and another line there. And the reason I'm doing that is because obviously a sine wave has a lot of symmetry. We see that not only is the sine wave symmetrical about this point, the part here is the same as the part here, except it's negative or positive. But there's more symmetry than that, isn't there? Because this point here is 1/4. This point here is 1/4 of t, where t is the period, which in this case is pi seconds. So this is actually pi over 4, isn't it? Yeah. So this is pi over 4. This, of course, is pi over 2 here. So if you think about it, if I want to know, probably need another color for this one. If I just calculate this amount of time, however much time this is, then the total time for which we're on this red part is double that delta t, and the total time including this and this will be 4 times that delta t. Yeah? So what that means is, because of this 4-way symmetry in the modulus of the velocity, yeah, we really just need to calculate 1/4 of the necessary time and then multiply it by 4. Okay, so I've tried to explain that as carefully as I could, but I realise that it's often a bit difficult for people to follow. So I'll show you the calculation, and hopefully you'll kind of get it from that. And if not, maybe just review it. Now, so if I were faced with this question, I would simply write, okay, T1 is inverse sine of 2.4 over 2.6, because obviously this is a sine wave with an amplitude of 2.6, so it's basically inverse sine 12 over 13. And the time that I want is going to be so what am I doing? The time. Oh, I see. Yeah. So the time that I want is, so let's call that delta t. What I've written as delta t here is just pi over 4 minus that. So total time is just 4 times pi over 4 minus inverse sine 12 over 13. So that's something we need to check on a calculator. Okay, I've just double-checked my calculation, and I actually made a really important mistake there. It's a good example of how things can go wrong. The problem I had was that I kind of jumped a step. When I wrote this, I missed something critical. There needs to be a 2 here. Now, maybe you weren't sure why I wrote this anyway, but if you did see my mistake, then well done. My mistake was that what we're doing is we're using this equation to find the value of T1. Yeah? So V is, if V is 2.4, we're writing 2.4 equals 2.6 sine 2 T1. Yeah? So that gives T1 is actually 1/2 of inverse sine 12 over 13. So let me just slightly rewrite my calculation so it's correct. Sorry for that silly mistake there. So we need a 2 here. 2T1 is, whoops, 2T1 is inverse sine 12 over 13. So well, let's just say T1 is half inverse sine 12 over 13. So that's that minus 1/2, whoops, of, so that's T1 there. This is our formula for T1. Yeah, so this was pi over 4 minus T1, and then we need to multiply that by 4. So this is the formula here, and this gives the right answer, which is 0.79 seconds to 2 decimal places. So that's the final answer for that question, 0.79 to 2 decimal places. So that's that question complete. Okay, so there are 2 more examples I want to show you, and these are significantly more difficult. These are real questions from the further maths exam, and they're quite demanding. But more importantly, the topic of these 2 questions, here's the other one, is the topic of approximate SHM. So SHM approximation, which is explained here, which I actually did describe a little bit in the first video, but I think because they'll take a little time, I'd rather postpone that to the 3rd video in this series, so that the video after this will be about exam questions using approximation for SHM. So thanks for that, and see you next time.